So continuation of previous topic. Previous class we discussed what is electric field. Now we can analyze the electric field. Okay, and there's a basic concept about electric field. Suppose when you move a test charge, actually we consider when we move a test charge, what happens when we move a test charge and the charge object, test charge around the charge object to measure electric field, measure E in a surrounding by the charge body. In the surrounding by the charge body. Field is independent of test charge. We have discussed field is independent of test charge. So if some consideration, can take an example. If there is a plus 10Q charge, so consider a plus 10Q charge, and here is an consider a minus 1Q, or say that is 10 coulomb and 1 coulomb charge. Okay. Now tell me what is the field at here, at that point. Okay, at that point actually field in that direction. Okay, field in that direction, because the 10Q charge electric field, and that is a minus Q, so E obviously on that direction. Okay, E actually in that direction, and E depend on K Q by R square, means that if R is increased, so electric field obviously decrease. If R is less, means the R is less, so electric field is increasing. Okay, so here the some value of R at that point, electric field in that direction. Now consider at here, at suppose to at that point, so electric field in that direction. Okay, why? So now we can draw that if that electric field here in that direction. Okay, but actually when distance is increasing, okay, so field is decreasing. That is a more powerful, that's plus 10Q the respect to the minus 1 coulomb. So we see that is in that direction. Okay, and here at some point here, okay, and here you see that also some here, but against that, after that, they not back here, they actually go here. So similarly that the field is now look like this. Okay, so you see that at point here, at that point, this region, the electric field in that direction. Okay, because that's a green color is called field line. This green color line is a field line. So what is field line? Suppose consider a tap, okay, a tap and the water flow from here. So that is the water flow. That is a path. That is the path of water flow path. That is the water flow path. Now I draw a tangent here. That is the direction of water flow. Okay, the direction of the water flow at that point direction. The direction rapidly change. Direction is rapidly change and depend on the position of the path. Okay, if path is bending, so obviously direction is bending here. Similarly, in that case, if I choose the electric field at that, so that in direction. If I choose electric in that direction, but if I choose electric field here, that is opposite direction. Okay, so and in between these region is called a neutral region. This region is a neutral region. Neutral region means the electric field is zero at that region. Okay, so Michael Faraday actually concept that field lines. Okay, and that the tangent at any point of the field line that represent the electric field at that point. Okay, electric field at that point. Clear? Now, that is the electric field line. And electric field line is given an electric field strength. Another important concept. If I draw some region, okay, some say that that is a region. That is a yellow color region. Okay, some consider that is the boundary of yellow color. That is the boundary of the yellow color region. Okay, and see that the region some 1, 2, 3, 4 and or 5 field line crosses that 5 field line crosses that yellow color region. When this field line length is field strength, actually that is the field strength depend on number of field lines by area. If more field line is less area means more field strength. Actually see that here at that region area is more but number of field line is less. That means weaker region. That is a weak region. Weak region and that is strong region. So means if that it's near the charge, source charge, the field is strong and the distance is increased. You see that is if distance is increased, electric field is obviously the weak. So R increasing means the field is weak. That is the field strength. And here you see that is a long distance here. That is a weak field of this more long distance, more weak field. But at that some any point there is a neutral region. Okay, so how to describe that? Where electric field strength actually electric field strength depends on the number of field lines. Depends on number of field lines crossing a unit surface or area. Crossing a unit surface area. Okay, and field line invented the Faraday's concept. Okay, concept of electric field line. And how do I calculate that neutral zone? Okay, if say that as neutral zone calculation, suppose say that two charges, consider that is a plus Q1 charge and some distance we get another charge is plus Q2. That one is test charge, one is the source charge. So suppose if both charges are positive, so actually field lines now look like this. So if both are if that is a 10Q, that is a 1Q, so means is that look like this. Okay. and the Q2 is a weak, so that's the weak region means. And in between we get a neutral zone. Suppose there is a Q charge, another charge is that another charge Q1 and Q2, and there is a separation Q2. If Q1 and Q2, you may consider Q1 and Q2 have the same charges. Okay, if I consider that both have a same charges element, so the electric field at that point P. So calculate that point P, electric field at here point P. So if Q1 actually in that direction field, okay, due to Q1 field at point P in that direction, that is E1. Similarly, due to Q2 field in that direction, that is a E2. So if the distance is R, okay, the distance is R in both cases, or both are the same. So, distance is that is that R, both cases. So E1 that is equal to K Q1 by, that is the direction displacement vector 1 to 2. So R1 2 cap. So here E2 same K Q2, the displacement R, and that is in that direction R21, but due to U2 both have same the dispersion vector R21. If I added these two at point P, that's a vertically added, okay. So if I added these two, E1 and E2, so E1 plus E2, so that is K, I would say that is a Q1 also equal to Q2. So that is Q by R. So R12 cap plus R21 cap. Okay. So that is very easy. And that is the magnitude. So that is the vector. And say that is also the vector. That is a K Q by R. And we know the R12 and R21, they are opposite. So R12 and R21 now represent the R12. That is the opposite. So they cancel. So K Q by R times 0, get a 0. So total field at point P, that is we get E total, that is equal to 0. And if I say that is a magnitude of E, that is a E1 magnitude, and R12 cap, and E2 magnitude, and both magnitude of same. If I say that both are same, the direction may be the different. R21 cap, the direction. So we get the neutral point. So if when the at point the electrical is 0, so this point is called neutral point, and this zone almost is called neutral zone. Okay, that's very important. So at neutral zone, E neutral, we get electric field is 0. That's very important. The zones is said to be neutral. Okay. Now we can now try to calculate, that is the electric field line. Okay, that is the electric field line, and there the field line has some properties. Okay, field line have some properties. So property number 1, that's the field line property. Property number 1. This is a continuous curve. Continuous curve from plus to end minus. Okay, that is a continuous. Property number 2, starting from positive to negative. And point number 3, they do not intersect each other. or cut each other. Why? That's very important point. If some say that if I cut these 2 points, okay, say that that is a one field line and field line these two cut. So I will tell that that is a field line represent the path of electric field. Okay, an electric field is a vector, field line is a scalar. Field line represent the path of electric field, like that is tap and water. Okay, water flow, that is the path, and at any point of that flow you can draw a tangent. That tangent represent the direction of water flow. That is a vector. So at tangent at any point on the field lines you get a electric field at that point, and always be the in any direction. Okay, so direction may not be equal. Okay, may not be, and there is always may not be equal. There is always not equal. Okay, if they are equal or they are intersect, if they are intersect, if say that they are equal, okay, if we say that they equal, if I say draw tangent at that point, if I say tangent at that point, so their direction may be equal. Okay, but and if they are intersect, if field line they are intersect, okay, if field line they are intersect, so get a two tangent at that point. So one tangent in that direction and a tangent in that direction. So one point gives two electric fields. That's like a bogus concept. Okay, that means that is one point gives us only one electric field direction, not two electric field direction. Okay, two electric field. That's why they intersect field lines. They do not intersect each other. Okay, but they in opposite line they have same tangent sometimes. Okay, if I draw, it's possible to same tangent, same tangent. So they possible the same direction of it, not same tangent. They possible in same direction, but they do not possible they cut and get the same direction. If they intersect, you get get two tangent or three tangent. That is no, that is always true. They do not follow the one only. They always independent. Okay, they always follow haphazardly. Okay, say one point gives three electric field direction. Okay, they do not follow. Okay, to follow each other. So they are independent. So that's why they do not intersect each other, because one point gives one field or one field strength, or so one point gives one electric field here. Now another important concept, calculate the electric field at Q1, that is only one source charge and one test charge. Yeah. And you can say the one charge body, previously discussed, one charge body and that one test charge. Now calculate the system of multiple charges. If a system has the multiple charges, what will happen? Calculate the electric field. Calculate the electric field. So system of multiple charges. Of multiple charges. Suppose we consider that is a diagram here. You see that is a one charge plus Q2, charge is plus Q1, and that is plus Q3. Okay, and that Q1, Q2, say that Q2 and Q3, these two are the source charges, and Q1 be the test charges. Q1 be the test charges and Q2 and Q3 be the source charges. So calculate the electric field at point P, calculate at point P due to Q2 and Q3 source charges. When we calculate the electric field at point P, the first step is that bring a test charge, any test charge, either positive or negative, at that point P, and calculate the force at that point P, and then we divide the force by test charges. So we get a total electric field. So electric field at point P due to Q2, obviously in that direction, E2, and electric field at point P due to Q3 in that direction, that is E3, and that the displacement origin, that is if I draw a x and y, that is the origin point OO, that is the position vector of R2 for Q2 position vector, that is a R3 Q3 position vector, and that is point P, say that the R position vector. So that is the displacement vector. Okay, that is R2 to P direction, and that is the another, say that R3 to P direction. Okay, so say the total electric field in that direction ET. So by ET or E1, now choose any arbitrary point and draw a parallel E3 to cut at E2, and this green color line is parallel to E3. So E3 and green color line both are the same, that is E3 vector, that is the E total. Now we calculate that vector triangle law. So triangle A, B and C. Calculate vector triangle law. So clockwise taken positive and anticlockwise taken negative. So that is the A, actually BA as clockwise, and AC is anti-clockwise, that is a C, and CB. Okay, so CB, that is basically the anti-clockwise direction. So we say that that is a E1 plus minus E3 and minus E2, that will get a 0. So E1 or E total, that is equal to, that is E total or E1, that is E2 plus E3. So you can see that they obey the superposition law. Superposition law, just simply algebraic addition. Okay. So E2 means that K, the Q2, the source charge, by RQ2 means that R2P, 2 at point P square, R2P cap, uh, 2 1, say the 2 1 or 2P, okay, both are the same. And K, that is Q3, and E3, that is Q3 source charge by R3P square or R3P cap or vector, that direction. Now common these two K, and we finally get a Q2 by R2P square R2P cap plus Q3 R3P square 3P cap, and the summation is that the K, the summation I equal to 2 to n, just added. Okay, so that is Qi by source charge by 2, sorry, R I P square R I P cap, that is the E total. Let's get the final answer. Okay, there is system of multiple charges. How to calculate electric field? That is a vector. Okay, if I choose a plus, minus, all that is very easy. Okay, if you know the vector algebra, then you can solve very easily. Okay. Okay. Now, so now we calculate some, discuss some basic. Okay, previous topic. Okay, extension. Okay. So if I consider a charge sheet, Yeah, that is a charge sheet. Consider the charge sheet. There's all other sheet have plus charges, charges, plus charges. If I put a test charge here, a positive test charge here, so electric field in that direction. And if I put a negative test charge here, so electric field in that direction. Due to this, actually due to this in that direction, but actually feel like to this. It's actually electric field here to this, but here that is electric field look like this. That is okay. So you know that is what is texture and how the electric field look like this, and so if you want to calculate field at any point, the first step is always remember that bring a test charge at that point, then calculate. Okay, bring a test at that point and then calculate. That's the important. Okay, then here we see that that line also. Okay, we have bring a test charge. If you want to calculate field at point here, point x, so bring test charge at that point x, then you can finally calculate electric field at that point x. Okay, so clear. So always remember when you want to calculate electric field at any point surrounded by the source, always remember that it being a test charge either positive or negative at that point. Now you can calculate that electric field, and remember that the electric field is always independent of test charge. Okay, and electric force is a push and pull, but electric field is an abstract property. The difference is that of force and field. So force and field difference is the electric force. Do not if you have a doubt, maximum can have a doubt. Okay, what is the force and field? Both have same. Okay, do not confuse that. The force and field, the electric force, is a push and pull. Is push or pull, but electric field. Okay, electric field. Field is an abstract property set by the charge body. Is abstract property set by charge or source body. Okay. Do not confuse that two point. What is electric force and what is electric field? Electric field have electric field lines. We know that. Okay. And if I consider some take an example, if a positive charge, here is another positive charge. So field lines look like this. That is because that is positive field. Hmm. So here is the neutral zone. Here is the neutral zone. That means the electric field is zero. Okay. Here the neutral zone. And if one is positive, another is negative. If one positive, another negative, it look like this. If one positive, another is negative. So electric field now will look like this. Positive to starting from positive field lines and ending to negative. There is a bulging. Okay. Okay. Now clear some basic concept. Okay. So take some example here. So there is a plus 8 coulomb charge. Here is a plus 20 coulomb charge. Okay. So how the where the neutral zone stay? Actually, neutral zone here, if both are in plus, so if a means 20 plus is more powerful than 8 coulomb, so neutral zone to weaker zone region, weaker charge region. Okay, that is a neutral zone. Okay. And how the field lines look like this? If look like this plus to if both are like charges, so neutral zone always be the at in between two charges. If a negative and negative, okay. Now just means just only direction with the different. Otherwise, both are same. Now, if one charge is the plus 20 coulomb, here say that minus 8 coulomb. All of where the neutral zone present. If both are in different, so neutral zone always present towards the less charge region. So if both are in opposite polarity, so that is outside that charge. So here that is a neutral zone. And before the neutral zone, electric field is in that direction. Otherwise, neutral zone in outside direction. Now we'll now look at that is plus to minus. Draw the fresh page here. The full page. Need. Mm, mm, sorry. And field lines look like this. Okay, that's very important. Okay, so today end the class here. Clear the concept of electric field and what is electric field lines. Next class we discuss the dipole. Okay, so thank you.